Welcome to Agents of Tech, the podcast where we explore cutting-edge technologies shaping our world today, from big data to quantum computing, from AI to robotics. We delve into the ways that we can meet some of society's biggest challenges. Welcome back, everyone. I'm Autria Godfrey.
And I'm Stephen Horn. So, Autria, have you dusted down your snow boots now? Are you back home? Are you finally warm again?
Yes, finally, after that wonderful trip to Minneapolis for the American Physical Society's annual meeting. We had a lot of fun, didn't we, Stephen? And we really talked to some pioneers in the field of quantum physics.
Do you know what we did? We had a great time. We got a great show today because we're going to set up the next year, which is the International Year of Quantum. It's 100 years, Autria, since discovery of quantum mechanics, 100 years. So we're going to be having an interview on the organisers of that year, and then a really interesting interview that I did with Stuart Parkin, who revolutionized memory, and all the big data that we have today is all down to Stuart Parkin. So we've got that to look forward to.
Yeah, your interview with Stuart Parkin was so fascinating to me because he talks about how the disk drive is now 70 years old and how he has really kind of taken that and made it something that where we can store all of this massive data that we're collecting. But the fact that the disk drive is 70 years old just really struck me. I feel like that's still new technology. So a really fascinating interview that you have with Stuart Parkin. Lots ahead in today's episode, Stephen, but we actually want to get started with a really fascinating interview that you conducted with the chemistry Nobel Laureate Moungi Bawendi, who talks about quantum dots. And Stephen, I'll have to say, before this interview that you conducted, I didn't even know what a quantum dot was, but apparently they're all around me.
Well, they are. I mean, what's really fascinating to me about that, Autria, was the two things. First of all, it revolutionizes physics, a whole new way of looking at physics, but also the applications, because a lot of the time we talk about quantum computing, we talk about quantum this, we talk about quantum that, but what does it actually mean? Well, quantum dots, as you say, are all around us, and all you see as well, Autria. Let me start off by asking you a simple question. So what are quantum dots?
So quantum dot is a small nanometer-sized particle of a semiconductor, and it's small enough that when you put an electron in there, instead of behaving like a particle, like it would have in a wire, it behaves quantum mechanically. It fills the box with a wave, and as a result, the properties of those electrons are strongly size-dependent on the size of the box that you put that wave in. And it's those properties that end up being really interesting fundamentally, and really interesting from an application perspective as well.
So how did you get into this field in the first place?
Well, it was a kind of an accidental process, as many of these things are, right? So I was initially a theoretical polymer physicist or polymer chemist. Then I became a high-resolution spectroscopist in the infrared, looking at very small molecules in the gas phase of interstellar applications or interests when I was a graduate student. And then I had a fellowship from AT&T Bell Laboratories that allowed me to spend the summer at Bell Labs. Bell Labs was still around then. It was 1987. So I went there and I discovered the world of condensed matter physics and solid-state chemistry, which just opened my eyes to all of this incredible science and applications that was going on in electronics and optics that I had really no idea about. My summer was with Louis Bruce, a co-laureate, who had been basically working on quantum dots for about 5 years then. He had discovered the initial process, the quantum mechanical explanation of why these little particles behave the way that they do. And I just fell in love with it. Also, so then I came back to do a postdoc with Louis. What I really liked about that field was that it was brand new. So any question that you asked was a new question. There were no answers, there were just questions. So building a field from scratch was just incredible.
Tell us a bit about your major breakthrough in 1993.
So when I came to MIT in 1990, I had brought with me the beginnings of a way to make quantum dots that seemed to make much better dots than we had been making, that Louis and his previous co-workers had been making. But the problem was that it didn't happen all the time. It's one of these chemistry things that you don't know why it doesn't work, but so at Bell Labs, it happened occasionally that I would make these beautiful samples, and at MIT, it happened never. which was really problematic because my career hinged on me making samples. So we had to reinvent the way that we made our samples, based on insight that had gotten from being a postdoc at Bell Labs. So we developed a completely air-free, water-free synthesis based on old ideas of nucleation and growth, basically introducing precursor reagents very quickly into a very hot solution to get seeding, nucleation of very, very tiny little particles, followed by a longer growth step, which allowed us to control the size of the particle with exquisite precision. And then we followed that with what we call size-selective precipitation, which is basically purification, this is what chemists do when they create something new, a new molecule, you purify to extract it. And so that combination took us about 2.5 years from the time I arrived at MIT, and I wrote a paper with my two of my first students on that, Chris Murray and David Norris. And that synthesis is what allowed us to be able to really study the physics of the materials and open up the field to a lot of other groups that became very interested in physics, in developing further the chemistry, and eventually, not so long after that, in 1998, was the first startup based on quantum dots, the commercialization of the material.
Let me pick up on that. So what's happened since then, and what use are made of quantum dots today?
So since then, the field has grown exponentially. There are groups all over the world studying all aspects of quantum dots. The materials have exploded. Initially, we worked on one material, cadmium selenide, one semiconductor. Today, there's a lot of different materials. Also, little particles or nanoparticles that are not semiconductors that are grown in similar ways, like magnetic particles, semi-metals. So the fundamental science, the physics, and the chemistry has really grown tremendously, building what people call a new periodic table of artificial atoms, artificial functional nanomaterials that you can put together to create new properties. That's on the fundamental science part. On the commercial part, the big application that almost everybody probably has heard of is displays. The acronym QLED that Samsung has brought out, the Q stands for quantum dot. So it's the quantum dot that provides the green and red light in these displays.
That's fascinating. Now, the question I'm going to ask you now, you've been asked 100 times, I'm sure, but what went through your mind? How did you feel when you first heard that you'd won the Nobel Prize?
Well, I heard from a phone call at 5:45 in the morning, and the first, when you hear the phone ring at 5:45, you think something terrible has happened. And so my wife woke up suddenly and said, "What's wrong? What happened?" And so I told her it's from Stockholm, and then she knew immediately what I was talking about.
So amidst all this, what's next for you, and what's next for quantum dots?
For me, I'm very much interested in the quantum optics application, the potential quantum optics application of quantum dots. And since it's going to be the year of quantum, this is right in line with my interests, so it's very apropos. I'm interested in pursuing, some other potential applications also. And then I'm interested in reaching out to young scientists, and getting the Nobel Prize comes with a lot of joy, but I also feel it comes with some responsibility of telling your story. And the path that we all take in science is often one of frustration, but with amazing delight when something happens, and pursuing those delightful paths and keeping the faith and really following your interests, I think, is something that's really important to share with young scientists, because our future depends on them.
So let me follow up, just two quick questions to follow up with that. So when you come to a place like this, you know, there are thousands of people here and they're from all over the world. There's a lot of young people here. There were a lot of young people listening to you talk yesterday in the auditorium. They all want to be like you, so what's your message to them?
Well, my message is, you know, don't count on the Nobel Prize first. It's not what you strive for. You know, what you strive for is, you know, to feed your curiosity and to have faith in what you think is interesting is going to be really interesting. You know, keep that faith, because I think it's often a mistake if you're young to think that the only worthwhile directions are the ones that are well established, that have a big community, and, you know, that are fairly mature. But there's a lot of stuff out there at the edges that who knows what they're going to turn into, and those are going to be the next breakthroughs, the next Nobel Prizes. Those are worth thinking about.
Now, my final question is, everyone's talking about next year being the 125th anniversary, the year of quantum. So, and I think the UN is recognizing this. So what do you hope that's going to achieve?
Well, I hope it's going to achieve a realization that quantum is around us today, everywhere. Not just in displays that use quantum dots, but, you know, almost everything that we use as a technology in some ways has as a foundation the discovery of quantum mechanics 125 years ago. It's just such an important breakthrough in our path towards technologies. It's ubiquitous. But there's still a lot of things that we could do in quantum that will may be amazing in the future. So the next 10 to 20 years may see more amazing things relative to quantum information, quantum optics, things that really use quantum in ways that we haven't thought about before. So I'm very much looking forward to the next 10 to 20 years.
Autria, it's always great to chat to a Nobel winner, isn't it? And but that interview with Moungi I found fascinating, not just from the physics aspect, but also what he said. What I loved him saying, one of my favourite comments, Autria, was he said there's a lot of stuff to do. I like it when a Nobel laureate says that. There's a lot of stuff to do. It's something I can get my head around. And he's right, aren't there? There's so many discoveries that are still there to make. And you know who's going to make them? It's going to be the young physicists who are on their way through their careers. Audrey.
You're so right. And actually liked what a piece of his advice was to those up-and-coming physicists. And, he said discoveries come out of frustration. And it's, you have to try and fail and get frustrated. And then, boom, all of a sudden, you come across the discovery that you've been looking for. So I think hearing someone that's at his level and that's as successful and as lauded as he is, even say like, look, even I get frustrated, but I work my way through it. I think that speaks volumes to the next generation of physicists. Speaking of up and coming, next year, 2025, is going to be a big year for quantum science. It's the International Year of Quantum Science and Technology. So, Stephen, it's time to get our party hats, break out the birthday horns, because the way that they're describing this is we're having a big birthday celebration for quantum science.
You bet we are. It's the UN year of quantum. I mean, it's just going to be a huge, huge party. And, we sat down, didn't we, and talked to two of the organizers. I was really struck by a few things that they said, actually. I was really struck by they said that for this to work, first of all, it's got to be everybody's year of quantum and not just, those of us in the APS meeting, but also that it's got to chime with people's values. It's got to meet people where they are. And I thought that was really interesting. So let's take a listen. Claudia Fracchiola and Paul Katten-Zemansky, why now?
In 2025 will be 100 years since the development of quantum mechanics. And for those of us in the physics community and the physical science community in general, quantum mechanics has been a great friend over those 100 years. And we've seen tremendous developments, tremendous growth, and a tremendous future. And so we started talking to people several years ago with basically the pitch of, would you like to have a birthday party, 100 years for quantum mechanics? And immediately people said yes. We started calling up people all over the world, and we're like, yes, quantum's been a great friend. I want to have a 100th birthday party for it. So that's how it started, and more and more individual people came on board, more and more societies came on board. APS took the lead in this, but we have over 60 other societies, institutions all over the world who have been partners in this. And now we have many countries as well who are behind this effort.
So you've kind of discussed how the idea came to be. What will the year look like, and who are some of the key players?
So an international year is a process that gets declared by the United Nations. The idea behind it is to demonstrate to the world and create awareness about the specific topics, so in this case quantum, and then help build education and capacity, particularly on developing countries. It's an international year declared by the UN because the mission of the year has to support the Sustainable Development Goals of the United Nations. And then with that comes education, Africa, and women's representation.
And we should point out that there is currently a resolution working its way through the United Nations right now to declare 2025 the International Year.
Yes.
How quickly do we hope that that will be made official?
So this is a long process. It started with the UNESCO. So we started working with the UNESCO about a year and a half ago. The UNESCO General Conference that last May approved the resolution and then recommended to the UN to pass a proposition. So right now, the Ghanaian delegation at the UN is working with the Mexican delegation to get the item into the agenda, and we're hoping that it will be sometime in this spring that the year will be declared.
We have a lot of technology, a lot of technological innovation at the moment, haven't we? We hear about quantum all the time, we talk about artificial intelligence all the time. Let me just pick up on, Claudia, on that point that you just made. How do we make sure that the benefits of the 100th year of quantum are felt by everybody?
So this is a very interesting topic and one that, we're having across, and part of the conversations that UN wants us to have, right, is a matter of access, is a matter of supporting the capacity of developing countries to build their own quantum strategies, right? There's many things that the quantum will benefit, like the health system, the technology, the cryptography development and processing, all those things. So how can we guarantee that those countries also have access? There's companies that already are sharing their space time for developing countries to use what exists out there. There's not fully quantum computers, but what exists, to start testing it out. So the International Year looks to that, to help make sure that we provide equal access to everybody, and that everybody has access to the education that they need to build their quantum strategies.
And I would say that the biggest goal of the year is to just generate some awareness about quantum around the world. So in certain countries, in certain societies, like the word quantum is something that might be known. Some people might have some understanding about what that means. But most people around the world have never even heard the word quantum, right? And compare that to what people at this conference know. They know how central quantum science is to our understanding of the world around us. They know how central quantum science is to the technologies that underlie all sorts of things and have been developed over the past 100 years. And I think the main goal is just to make sure that more people around the world have even heard of that and even understand how central quantum science is to so many things. And that will help to move the needle in terms of bringing more people into the global conversation.
Young people are a very key part of enabling a quantum future. How are you making sure to engage with the next generation of quantum researchers?
So I kind of point out what the word quantum actually is well known in popular culture, right? Like last year, I think it was, Quantum Mania, the movie came out. So the younger generation have heard the word, right? And it's a matter of something idea abstract. What we're trying to do with International Year of Quantum is, build that campaign that connects with people's values on how quantum will really help their communities and their aspirations, career aspirations, to reach where they want. And part of that is, how do we demystify the word quantum? Right. Because there's a lot of misinformation about that word and what it really is. So the campaigns that we're trying to build around the International Year is demystifying that and making people comfortable talking about that and not as this abstract, weird thing.
It can be an intimidating word.
Super intimidating, yes, yeah.
Yeah, we want to be as friendly as possible, I think.
These are friendly quantum physics.
Yes.
But I really would like finally to pick up on that point you just made, Claudia, in terms of values, right? Which is, a lot of young people are really interested in that. And what I want to know is the success of the year. How will the success of the year make the world a better place through quantum? What can quantum do to improve the world?
Well, I think we have a 100-year track record of all sorts of things that quantum can improve. So just to pick up on a couple things, if you think about medicine, right? The physical sciences lead into all sorts of medical developments. So something that people are familiar with, like an MRI, right? A sort of basic diagnostic tool, which is spread more and more over the world. So one aspect of that is the actual resonance, which is a quantum effect that was discovered in the 1930s. The other aspect of that is that you need a giant superconducting magnet to make an MRI work. And that's a technology that was developed over many, many decades in the 20th century, right? If you think about something like energy, right? So solar panels, right? Converting sun's energy into electricity we can use. That was a quantum effect discovered around 1940, right? And developed over many, many decades. So we have a big track record of all these types of things that we've done with quantum. And if you're asking like, what's going to happen in the future? What future things can we solve? The answer is, we don't know. Right? We're researchers, right? And we're trying to develop more and more understanding and more tools. The other thing I'd want to emphasize, though, is it's not just about technology, right? I mean, a lot of people like technology. They think about, can technology solve future problems? But there are many people who are not interested in technology, who are skeptical of technology. But I think most people have an interest in the world around them. Just how does it work, right? Just asking basic why questions. I mean, every 3-year-old develops a skill to ask sort of why. And if you ask scientists that why question over and over again, the answers they'll eventually get to are probably quantum mechanical, right? And so for people who just want to understand a bit more about the world around them, regardless of technological advances and societal advances, but just sort of that basic understanding of things, which is fulfilling, like that's one of the goals of the year.
Incredible. We look forward to next year and all the excitement to come. Thank you for your time.
Thank you.
So really interesting information there from the organizers for this International Year of Quantum Science and Technology. And I think, like as you mentioned, Stephen, one of the biggest goals with this initiative is to just really try to get people talking about quantum science and realize how it's in our everyday lives and, how commonplace it is. We think of quantum physics as this, something that's so abstract, but really we're utilizing it in some capacity every single day. And something we should also point out is, as of right now, you mentioned that this is a UN initiative. We're still waiting for that UN resolution to kind of work its way through the system so that 2025 is declared like the international year. So fingers crossed that happens very, very soon because it's very exciting. Something else very exciting is your interview that you had with Stuart Parkin.
Mm-hmm. Stuart Parkin, right? So a couple of things coming out of Stuart Parkin that watch out for. First of all, you were right, okay, that the technology, the magnetic data is 70 years old. But from his discovery in the 1990s, he increased that by 1,000-fold. So the amount of memory that one could record, he increased that by 1,000-fold. Considering you have that on your CV, I've increased the world's amount of memory storage 1,000 times over, right? Isn't that incredible? And he said that all the data that exists in the world can now be stored because of that. And he's got a whole new bunch of innovation right up his sleeve to sort of take it to the next level. So let's take a listen to Stuart Parkin. So what is spintronics?
Well, spintronics is the concept that one can use the spin of the electron in various ways to create new devices that go beyond, for example, charge-based devices that form the computing systems of today.
So what got you into this field?
Oh, spintronics I started many, many years ago when I joined IBM Research in California, and they wanted somebody to do something in magnetism. And so I decided we should work on atomically engineered magnetic multi-layered structures, and it turns out they're the heart of spintronics.
And what's the problem that you're trying to solve?
Well, early on, this problem we wanted to address was how could new ideas, new materials, new physics help to advance magnetic data storage. When I joined IBM, they had a huge business in magnetic data disk drives, and they wanted to know whether we could develop new materials, devices, to enable them to continue to expand the capacity of magnetic disk drives. And the challenge was at those days was how many magnetic bits per unit area of the magnetic film in which the information was stored could we increase it by? And there are many theorists who said it couldn't go beyond some limit. So with spintronics, we were able to show we could go 1,000 times beyond the limits of those times. And so increase the storage capacity of a magnetic disk drive more than 1,000 times.
Wow. So what was your major breakthrough?
Oh, the major breakthrough was that we could develop new materials which are atomically engineered by combining ultra-thin layers of non-magnetic and magnetic layers, we could devise a structure in which a tiny magnetic field could change the orientation of magnetic layers and thereby influence the flow of spin-polarized currents. And so we could build a very sensitive detector of magnetic fields at room temperature and above, 1,000 times more sensitive than any other detector at that time and even today.
People talk a lot about data storage these days, and they talk a lot about it in terms of the next industrial revolution with data storage and kind of connectivity. And you've revolutionized data storage. How do you think that's impacted the world since you had your discovery?
Well, I think that because of these spintronic devices, we can store enormous amounts of data, and today we live in a digital world. We've already reached the world in which all the data can be stored in magnetic disk drives, and that has meant that we can create new businesses based on looking at that data in ways that were simply not possible before.
And what are you working on now? What's your next big thing?
So now I'm working on the technology which I believe could replace magnetic disk drives. Today, 70% of all digital data is still stored in a technology that is 70 years old, made possible by advances, for example, in our spintronic sensing devices. I'm working on a new technology, which I think is super interesting. I call it racetrack memory. And the concept there is that you manipulate data, you store data in nanoscopic magnetic spin textures, chiral magnetic domain walls, in tiny magnetic nanowires. And these nanowires, you store the information in such a way that you can move the data to and fro in the wires and bring the data itself to sensing devices or devices to write that data. So it's the only technology in which data is manipulated, is moved. And this is very important because then we can create a device that can store 100 bits of information or maybe 200 bits of information and increase the capacity of a memory 100 times as compared to charge-based memories of today. So I believe we can replace magnetic disk drives in the near future with magnetic racetrack memory, which will be very high performance, 1,000,000 times faster to read the first bit. It'll be 100 times more energy efficient and much more capacious, much less volume to store all that data.
And what impact will that have?
Oh, well, first of all, it'll save an enormous amount of energy. We'll be able to build devices that are much more compact and smaller. It'll be more reliable. And for all these reasons, we'll be able to then store even more digital data and access it even faster. And therefore, for example, the major advances of today in machine learning and artificial intelligence, which are basically fundamentally based on access to data, will be even more powerful.
Let me ask you one final question, if I might. A lot of young people gathered around us here in Minneapolis. What's your message to the younger scientists of today?
I think, well, my message would be that one should try to do the impossible, that one should, I think a lot of the most difficult things take a very long time. So for example, magnetic racetrack memory, I started working on 20 years ago. But it's a relatively small field, but I think it's super interesting. We've developed and discovered so much new physics that wasn't even thought about 20 years ago. So I think one has to be one has to have an idea and one needs to follow it. You need to have a belief in something and then follow it, even if one doesn't know the way to achieve that goal.
Thank you ever so much.
Okay, thank you.
You know, sometimes when you think about memory, and you think about magnetic tape and memory, it's not the sexiest of subjects, right, Autria? You don't think, wow, I really loved listening to somebody talk about memory. But it's really inspiring what Stuart had to say. Because you think about it, all the big tech companies, all the Googles and the Amazons and the Apples, and talk about AI and all the usage of artificial intelligence, it would not exist without what he's done for memory.
Right. It's incredible how everything he's created is applicable to our day-to-day lives. Like, we're using it every single day. We pick up our phone and want to save something to storage. So thank you to him for everything he has created, because it's made our lives much more manageable and easy. That does it for today's Agents of Tech. But coming up on our next episode, a very exciting sit-down interview with Physics Nobel Laureate Pierre Agostini. Stephen, you were able to sit down with Anne Lhuillier in our last episode to talk about her award-winning work. But, Pierre's working on the same stuff alongside Anne Lhuillier, the attoseconds of light. So he has been awarded for his work on that as well. So you actually get to, once again, sit down with him and talk about his award-winning research. And plus, we'll also focus on advances in quantitative MRI for studying the aging brain, which I think is something that we are all very interested in. We want to have, brain longevity, try to keep it in tip-top shape as we age. And then, of course, we'll get into the development of a large-scale quantum internet and really discuss whether or not this is even possible. So a lot's on tap for our next Agents of Tech. Make sure you subscribe to the Agents of Tech podcast on YouTube, Spotify, Apple Podcasts, any of the other platforms where you get your podcasts. Until next time, everyone, I'm Autria Godfrey.
And I'm Stephen Horn. Until next time, it's goodbye.